Hello, I'm Alex Henning, and today I'm going to talk to you about how we use physical continuous integration at Fetch Robotics to ship robust and reliable robots to our customers. So, when I started at Fetch Robotics a little over a year ago, we were using a lot of existing best practices for software development. We were using continuous integration for software with build.ROS. We were doing code reviews on GitHub. We were using ROSLint to check our code. But it was still very time-consuming and took a lot of manual effort to get a release that we were happy with to ship to our customers. And one of the reasons it was so time-consuming was we had to verify that the robots behaved appropriately in a realistic environment. And if we found a problem, it was a very slow feedback cycle to go back, develop a fix, go through the testing process, and get a release. And we found that a lot of the problems that were causing the slow feedback cycle were due to the interactions between the software and the real world. And we really wanted to be able to quickly release robust and reliable software for our customers. So we took what we were already doing with regular old software continuous integration and added real robots into the mix and started doing physical continuous integration, where we tested every pull request on real robots in a test warehouse. So at Fetch Robotics, we were testing that FetchCore, our fleet management system, gets robots to the right location at the right time and keeps them fully charged so that pickers can place items on them and ship them, send them to a consolidation area. And we're also testing that robots like Freight can autonomously navigate safely and smoothly in a warehouse environment in a way that people are happy with. So our test setup is a 7,500 square foot test warehouse that we have in San Jose. The front 2/3 are dedicated to longer term release testing, and the back 1/3 is dedicated to actually building pull requests from GitHub and testing them on real robots. We have over a dozen robots in this facility and 16 ceiling-mounted cameras that give us a view of what's going on in the warehouse at all times. We also have a number of servers for recording bag files and for recording video from all of the cameras in the warehouse, and for running FetchCore to communicate to all of the robots in the warehouse. So now we're going to go through the process of what happened when you want to test a change in a physical continuous integration setup. And so at Fetch Robotics, we also want to make sure that the version of ROS that we're shipping to our customers is robust and reliable with our software. So we take a snapshot of the release Debians, and we always test that before we release that snapshot to our customers. And so a few months ago, we pulled in the latest changes. We did the regular local testing, and everything seems to be working. So we started up some physical continuous integration to run our code with the latest ROS for a few days. And after a few hours of testing, we started getting some notifications that robots were refusing to move. So luckily for us, our physical continuous integration setup is always collecting a lot of data so that we can actually dig in and figure out what's going wrong and look into it. And our robots are always bagging whenever they're moving, so we have access to any data that's being published on a ROS topic. They're logging what's going on. The cameras are always being recorded as video so that we can go back after the fact and look at them. And we have tools to actually sift through all this data and get the relevant data so that we can actually find what we want to look at and dig in. So in this case, when we pulled the logs from the robots that were stuck, we found a message like this, where basically the global plan was in collision and the robot was replanning. But we kept getting the same message over and over, and normally you'd expect it to plan around an obstacle. But in this case, it wasn't. So once we found this log message, we pulled up the cameras and looked at the test warehouse to make sure that there were no obstacles that we didn't expect. And at this point, when we looked at the cameras, the test environment was in a good state, like we expected. So we pulled down the bag files for the robots that were getting stuck and started playing them back in RViz. Before I go too much into detail of what we found in the bag files, I'm going to give you a brief introduction for cost maps for those of you who aren't familiar, so that you can understand what we're going to look at. So cost map 2D is part of the ROS navigation stack, and it's used to help plan collision-free paths and avoid crashing while following those paths. The image you see here is what a cost map looks like if you visualize it in RViz, and the yellow corresponds to an obstacle, and obstacles can come from either sensor data or maps. Usually you combine both to actually look at, to get the obstacles. The teal corresponds to an inflated obstacle, And that's used for collision checking. If you have a circular robot like a freight, you inflate the obstacles by the radius of the robot, and then you can do efficient collision checking with a point model. And this allows you to actually do fast collision checking. But you can use cost maps for non-circular robots, just a bit more slower. And the red that goes to blue is the red is the highest cost that's not actually in collision, and it fades out to blue, and eventually the clear that shows up as gray here, that's free space. And this is what you would expect a cost map to look like if you were using cost maps in the past and when it was bug-free, and it's going from obstacle to high cost to low cost. But when we started looking through the bag files, we found lots of cost maps that looked something like this. And you can see that the yellow obstacle goes straight to free space in some places, and there are other places where the cost doesn't go out smoothly and it just goes straight to free space. And this is what was causing, and when we started looking at the bag files, this is what was causing the plans that were in collision, is it wasn't inflating, the inflation wasn't there, so it was planning paths thinking, oh, this is free space, I can go here. But in reality, it was in collision. Luckily, a local planner was smart enough to realize this, so we didn't actually crash, we just got stuck and kept replanning. And so as we watched these bag files, we were able to get an idea of what the robots were doing that caused this problem. And once we were able to see how that was happening, we could reproduce the bug in a repeatable manner in our office and actually look at what was happening so we could develop a fix. And as we reproduced the bug and looked at the bag files, we were able to notice that it looked like there was an issue with the way that cost maps was updating. So as you move around, the cost map is incrementally updating a rectangle of where the data has changed, but it wasn't factoring in obstacles right outside the rectangle that needed to be inflated back in. And so we were able to develop a fix based off of what we had found while looking at this bag data. And once we had that fix, we could verify it locally and test it using the reproducible test we had been doing. And then we ran it through the regular software continuous integration and a code review process to make sure everything was reasonable. And so at this point, we were getting pretty sure that we had fixed the bug, but the bug had been introduced, had also gone through this process. So to really make sure that we had fixed it, we started physical continuous integration again. And for this, we needed to write a new test so that we could actually test for the actual root cause and not just the planning problem. So we wanted to actually detect that cost maps were always being inflated and incrementally updated properly. So we wrote a test that did a full reinflation of the cost map and compared it to the incrementally updated one so that we could detect the problem automatically and catch the problem and avoid regressions in the future. We tested this on the code with the bug to verify that it did in fact trigger when the bug was present. And then we started running continuous integration on our robots for several days in the test warehouse with this running continuously in the background to make sure that the problem was really fixed and that we would catch it in the future. And at the end of a few days of testing, the results were posted on GitHub and that the problem was not detected at all. The robots continued to move, and it also, the latest Debians at that point were also working. So since the problem seemed to be solved, it passed code review and all the tests passed, we merged it in, did a release so that everyone could have a version of cost maps that planned collision-free paths like it was supposed to without the bug that had been introduced accidentally. And at this point, we've kind of gone through the process of fixing a bug that physical continuous integration found before that we didn't catch with the previously existing automated testing. So you may be wondering, how can you actually take this and apply this to your robots so that you can do physical continuous integration and make sure that your software is working well? And at Fetch Robotics, we use a few different tools when we do this. So we use Ansible, which is used for configuration and orchestration of many machines. And this allows us to avoid manually having to set up all of the robots and servers in a test environment, which would be error-prone and time-consuming. We also use ZoneMinder, which is some open source software for recording video from all 16 cameras. It detects motion so that you can know when things are moving, and also only record video of motion, allowing us to get the most out of our 18 terabytes of storage. And we can have 2 weeks of video of all the motion in our test warehouse. In addition to those existing open source tools, we have a bunch of custom software that we use that ties it all together. So when a developer makes a pull request on GitHub, after it goes through the regular software continuous integration and the code review process, they can trigger the physical continuous integration process, and that will get queued up and run when the robots are available. And once that test has run, the results get posted back to GitHub with any relevant information. And it's constantly gathering data. And so you saw a lot of the data we gather when we walked through this cost map bug. So it's constantly gathering the log files, the bag data, the video, and storing it in a way that we can actually query it with our tools later. So we can find the data that corresponds to a specific robot at a specific time, or we can get all the data for all the robots during a time period to get an idea of what was going on in the warehouse at that time. And we can also, FetchCore has a concept of tasks where you can tell robots to do specific things, and we can grab all the data based off of a task and look at how that is related to what happened. So if you've implemented software continuous integration in the past, you may know that you usually use containers or VMs, and if somebody does something like introduces a bug that does rm-r/ and you delete the entire file system, life can go on. You report a failure, you throw away the VM or container, and the next test can spin up in a clean environment and start from scratch without any unexpected bugs. But when you're running physical continuous integration, you're on real robots that are in the real world, and you're not going to take your test warehouse, throw it away, and get a new one. So instead, you need to deal with some problems that would prevent you from getting back to a known good state. And so some of these problems are if a robot crashes, then you may need somebody to go look at it and get it back into a good state. Robots can become delocalized, in which case you'll need to use the camera system to relocalize them so that they can continue navigating. Robots can run out of battery, and then somebody needs to go plug them in, wait for them to charge up so that they can go back to testing. And you can actually get into physical deadlocks if your multi-robot planner has bugs where two robots stare at each other, waiting for the other one to move, and neither moves because they're both running the same code. And so any of these problems can basically cause the testing to not get back to a consistent state. And so in order to reduce problems of not getting back to a consistent state, at Fetch, we always do code reviews and software continuous integration before we start the physical continuous integration so that you can catch problems using existing testing setups like regression testing and unit tests before it gets onto the real robot. In addition, if a problem does slip by and and you start running into these problems, you can detect it and terminate early. For example, if your battery gets below a threshold that you know your charge management should never let your battery get to, you can terminate the test, upload any relevant bags for the developer and tell them that the test failed, and then you can load known good code onto the robots, have the robots go charge up to an acceptable level, and start the next test now that you've avoided letting the robots die from battery problems. You could also can detect if a robot crashes, and when one robot crashes, you report a failure and upload that failure instead of letting all your robots crash. And that way, you can have the other robots continue the physical continuous integration as you go on. So anyone who's shipping robots should really consider integrating physical continuous integration to their workflow. We've been using it for the past several months at Fetch Robotics, and it's helped us ship robust and reliable software a lot faster. But just like regular testing, it's not a silver bullet. If you're not writing tests to detect a problem, you're not going to catch that problem and it can slip through. So you need to actually think about how you implement it in what you're testing so that you're testing the bugs that you want to catch. But if you're shipping robots, you really should strongly consider using it. So we have a few minutes for questions. I think that one's broken.
I'm curious to know what your test cases are. Like it sounds like it would be sort of like a high-level smoke test, but I'm just wondering, what are the bugs that you've caught where you've said, oh, we need a new test case to cover this, and like how do you kind of like manage the suite, I guess? And is it something where the developer opts into a particular test, or is it feels like it would be very time consuming and resource consuming to run a huge suite on everything.
Yeah, it is more of an integration test than like a unit test. It's not, we're not building a unit test. For unit tests, you should be doing that all in software. And in fact, for this cost map bug, it really could be caught as a set of unit tests on cost maps. They just weren't there at the time. So you can basically, once you catch the bug in the integration tests, you can go look at what is the root cause and see, can you do it not during the physical continuous integration, but can you like do a regression test playing back bag file data to cost maps and seeing if the bug occurs. So in a lot of cases, you really do want to pull the tests out of the physical continuous integration if you can and do it as a regression or a unit test. In this case, it was just kind of an example that we found the problem and we verified it with physical continuous integration in addition to normal unit testing.
Cool.
Hi, Alex. I have a question. When you test the code, one way is to check the log file, and another way is to use a debug tool like GDB. And as your experience, which one is better and why?
Well, so this is like continuous integration, and normally you don't GDB into a continuous integration test. It's kind of if you're debugging a problem, when you're developing, you're going to be running it in your development environment and you can GDB in. When you're running it in the continuous integration environment, the continuous integration environment is going to continue on and start with the next test. And and usually you look at the logs, and in this case, we grabbed some extra data because we are in the real world, and text isn't always enough to describe what's going on. But if you need to GDB into something to debug an issue, you probably want to fire it up on like a development robot locally and not try to run it through the physical continuous integration system.
Yes, and which one is intensively used?
Can you repeat that?
Which one is intensively used in the practice?
I mean, we use both at Fetch. Like the physical continuous integration is an integration test to make sure that everything works. But if we find an issue, then we use both the logs that it provides, as in the example here, and we go back and reproduce it on a robot so that we can pull up and use tools like GDB if we need to.
Okay, thank you.
Hey there. So I'm curious how you manage the kind of size of your bag files. So I imagine, with your cost maps, if you had, a couple hertz of, uncompressed cost maps on all your robots, that could go pretty big. Can you just talk about some of your approaches to dealing with that?
Yeah, so we have all our ROS bags compressed. We also do, for some topics, we publish a throttled version and we record the throttled version if it's a fast update rate. Mm-hmm. But the big thing we do is we just have lots of disk space, because that way you have the data you need. Because otherwise, like when you need data, often you really need the data, and it's a lot more effort to try to reproduce the problem than to just get a few extra disks and have the data you need.
Right. About how much storage have you found you need for like a day's worth of one of your robots?
I don't remember the number for days. I know the server we have for bag files actually can store about a month's worth of bag files, and it's not nearly as big as the one for the video. So less than 18 terabytes for a month.
All right, thanks.
Oh, I have two questions. Okay. What was the biggest benefit compared to continuous integration in simulation, and if I compare to physical integration?
Yeah. So, I mean, they're not really mutually exclusive. You probably want both. Just like if you want the cost map bug, we could write it as unit test once we found the issue. The big benefit of physical continuous integration over simulation is that we get to test the closest thing we can to what we're shipping to our customers. And there are things that the simulation doesn't cover right now. Like we heard earlier, like Wi-Fi is a big problem, and testing that your robots handle Wi-Fi disconnects and reconnects. Right now, at least in Gazebo, is non-trivial. But like if you can test something in simulation, then you can add that to part of your regular software continuous integration and catch it sooner. But you still probably want the physical continuous integration to make sure that there's not anything that's not covered in simulation that could get through.
Okay, thank you.